Okay, the recording is on. Thejaswini, you can go on. Thank you so much
Uh,
for giving the talk.
Thanks a lot, Charles, for introducing me and inviting me to speak here. So I'm really happy to talk to about Parity Games to all of you now. So um, today my talk would be about, well, in general, the title says Parity Games, Stroller, Number, and more. So ideally, what I would like to do is talk about parity games and then argue why the Stroller number for parity game is a fundamental uh, feature of parity games or of parameter. And then once we do this, I also want to talk about some new algorithms that we have, which I think the Strahler number part of my talk will inspire and say why we need these algorithms despite having so many other ones already. So that's the general idea of the talk that I'm going for. So maybe before I start talking about Strahler number, it makes sense to, well, define parity games and, start slow from there. So parity games is a two-player game played on a directed graph where the vertices are partitioned between two players, whom I will call Steven for the even player and Audrey for the odd player. So now, other than this, there is these vertices have some priorities, which are natural numbers from 1 to some d, which are assigned to each of these vertices. So in this example, you can see that there are the following priorities. For instance, this vertex has priority 2, and then this vertex here has priority 3, and so on. Now I've denoted Steven's vertices with a square and Audrey's vertices with a triangle. In case you want to remember, Steven is the even player and square has four sides. So, 4 is even, so it all comes together. Now, how is this game played on this graph? So you have a token which is placed at a start vertex. So in this example, let's say it's placed over here. And whichever player owns this vertex chooses the next move. So here, Steven owns this vertex. So Steven can pick an edge which goes out of this vertex and move the token to there. So there is only one edge here. So Steven doesn't have really much of a choice. So he moves to this. So the token moves to this vertex with priority 2. Now it's again Steven's turn because this vertex, this 2 is also owned by, well, Steven again. But Steven has more choices here because he can either choose that edge or the other one to go to the next, to move the token. Let's say, for instance, that Steven chooses to move the token here. Now it's Audrey's turn because the triangle is owned by Audrey, and Audrey chooses the next turn where she can move to the next. She has no choices here, but let's say she does this. And now it's Steven's turn again. So let's say they just do this forever. So the game stays, it's an infinite duration game. And let's just, so in this example, we saw this was the play that happened. I'm just rewriting this. So, or if you look at this play, then you can see that the priorities 2 occur infinitely often. So maybe now it makes sense for us to define what the objective of the players are. So the objective of each player is to ensure that the limb soup has the same of this infinite play row, let's say, has the same parity as whatever that player's parity is. So what this means is the limb soup, say for instance, of this play is 2, and here this limb soup is even. So Stephen wants these kind of plays where eventually you see vertices, the max priority of the vertices seen infinitely often is even. And Audrey wants the dual of this, where she wants the max priorities of the vertices seen infinitely often to be odd. So let's maybe take an example of a play that's winning for Audrey. So let's say somehow that Stephen, instead of choosing to go right at that vertex, instead decides to do uh, this play. So it'll be this play road prime, I'm going to call it, will now see 3 2 and 2 infinitely often. And if you look at this play, the limb swap is going to be 3 because that's the highest priority that occurs infinitely often. So that play would have been winning for Audrey instead. So there is, it's well known that parity games are positionally determined. Well, what does this mean? If at all Stephen has a strategy to win, then Stephen has one where he doesn't have to think, like look at the history and can, every time he's at a vertex, he just picks one edge all the time. So if you look at this game, especially, you can see that uh, just a minute, by always picking this edge, and this edge, Steven can in fact win from all vertices in the top half of this game, no matter what Audrey does. Like if the game starts in any vertex in this top half, then Steven can win by just doing these. Whereas um, Audrey, on the other hand, can win in the bottom half, and she does this by picking similarly this edge and this edge and this edge. So this is something we will take for granted throughout and use in the rest of the talk. So now maybe it is time to move on to why we want to look at parity games. There are many reasons why, but maybe if you look focus solely on the uh, complexity theory aspect of it, we know that solving parity games is in this interesting class of NP intersection co-NP and also in UP intersection co-UP. But it's still not known whether there is a polynomial time algorithm that solves this or not. And as I'm sure most of you are aware, uh, there was recently a breakthrough in 2017 where they reduced the runtime of the fastest algorithm for parity games from exponential to quasi-polynomial, and this was by Kalou, Jane, Kosinian, Lee, and Stefan. And well, now the natural question for us to ask is, well, can we do any faster? And if my answer was actually yes, and we significantly improved from quasi-polynomial time, I would be much more famous than I am now. So unfortunately, since 2017, we're still stuck at quasi-polynomial time. So, but we would like to see if we can do faster. And one way to do this is maybe revisit all the quasi-polynomial algorithms that have been given since Kalud et al.'s algorithm, and see what they all have in common and what they do and what they don't do. And that's exactly what we're, well, not in detail, but that's what we are hoping to achieve in the next half an hour of this talk. So let's maybe have a very brief look at how do many quasi-polynomial time algorithms for parity games look like? Well, here is a picture, and also note the use of the word many here. It's there for reasons. So my claim is that, well, not my, many people's claim is that many quasi-polynomial time algorithms look like the following. So they take as input a parity game with, say, n vertices and d priorities. And what they do is when they run this algorithm, somehow this algorithm has embedded in it something called a universal tree, and uses this universal tree as an underlying search space to produce a solution. And well, you might wonder why I started talking about parity games and now I'm talking about trees. So to somehow show that every parity game somehow has an underlying tree structure, I'm going to define something first. And that is what I would call an attractor decomposition. So an attractor decomposition can be defined as follows, but before that, I want to define what an attractor is. And I think this is a very natural concept in any like game played on a graph. So here you have a set, which is the striped set over here. Let me call this is the set I'll be referring to. And if I want to compute Stephen's attractor to this set, it will be this bigger set that contains this striped bit. But what is this set? Well, it contains all vertices from which Stephen can force the play inside the striped set with infinitely many uh, moves. So, for instance, if Stephen had a vertex over here, and the there was even one edge inside this striped set, you know that this would belong to the Steven attractor. Similarly, if you have an Audrey vertex and then all of her edges somehow pointed towards this striped set, then that vertex will also be a part of the Steven attractor, because whatever she does, the next move she will belong to that, like she'll go into this striped set. Now we compute such one-step attractors until it stabilizes to form the attractor of any set. So, like, I'm sure attractors are natural and easy to understand, but what we want is something slightly more, and this is what we will call an attractor decomposition. And what I will define is a Steven attractor decomposition, but Audrey attractor decomposition is similar, so I will stop there. And this attractor decomposition is parameterized by the top priority in some sense. So here I'll say D Steven attractor decomposition. So for this example graph, it will be 4 Steven attractor decomposition, because 4 is the highest priority in that game graph. So what is it supposed to achieve? What is this weird thing that we're talking about? So you can think of this as some kind of witness to the fact that Steven is winning. So if someone came and gave you an attractor decomposition, what you want to achieve is some kind of witness to the fact that Steven wins in every vertex in this sub game, or like so if you look at the set of all vertices that are winning for Steven in a game graph, you should be able to provide an attractor decomposition for it. And if you can provide an attractor decomposition for it, you can easily come up with a winning strategy and so on. So what is an attractor decomposition? Well, it is some kind of partitioning, recursive kind of partitioning of a game graph as follows. First, a 4 attractor decomposition, or maybe, yeah, a 4 attractor decomposition will look like the following. You take all the vertices of priority 4 in this subgame, and then you compute its attractor. If it turns out to be the whole game, then you know that this is already a witness to the fact that all vertices win for Steven, right? If Steven can always see the highest priority by like taking this attractor strategy, then he can see 4 infinitely often, because if the whole game is just 4 and its attractors, which have priority smaller than 4, then this is clearly a winning set for Steven. If not, if this is the case, then the attractor decomposition is defined naturally, where you just say the partition is just as follows. It's the set 4 along with its attractor, and that's my Steven attractor decomposition. The more interesting case is when you know that this whole game is winning for Steven, but the attractor to 4 is actually a much smaller set than the whole game. So if that is the case, what you do is you remove 4 and its attractor, and we claim that if the whole game, every vertex in this game was in fact winning for Steven, then you can recursively partition the rest of the game, like 4 along with Steven attractor to 4 complement. So the rest of the game as follows. You partition it into winning regions for Steven that look like the following. So these are winning regions that have priority less than or equal to 2, followed by an attractor of Steven to this. This can have priority less than or equal to 3. And then another set of winning regions for Steven with priorities less than or equal to 2, followed by an attractor of Steven of like priority less than or equal to 3, and so on. So, well, this was a small example where we just had 4 and like only 2 even priorities. But if you had, I don't know, let's say 8 over here, then what would happen is this would be 6 and this would be 7. And since this is a winning region for Steven with priority less than or equal to 6, it will have its own Steven decomposition. So you'll have a recursive structure in there. So now what we can do is, given such a, maybe it's good to look at this on an example, and that's why I have this here. So here we look at a 4 decomposition. So we look at all the vertices of priority 4, look at its attractor. It turns out that actually there is nothing in its attractor, because there is none of these vertices can be attracted there. In the rest of the graph, you want to partition it, as I said before, into winning regions with priorities at most 2 for Steven, which conveniently looks like this for us. So I can draw a partition. And then if you look at its attractor, that would include this vertex 3 and vertex with priority 3 and vertex with priority 1. And this will have its own decomposition, this bit, since it's a winning region for Steven with priority 2 and 0, it will have its own decomposition. We'll come back to it. And then this is the second recursive subbit we have here. And if you look at the decomposition of this, that would just look like 2 and its attractor, and then 0 and its attractor, and so on. So this is not it's not ideal, but I hope it's. So now we know what an attractor decomposition is. We can talk about a tree of an attractor decomposition, and this is where the trees come in. So we took a huge detour, but I think it was worth it to spend time on that. A tree of an attractor decomposition can now be defined very naturally. Sorry, someone.
Yeah, just a quick question about your example.
Yeah.
So you have like 2 of these regions, winning regions of priority at most 2.
Yeah.
What made them, like, why does the decomposition make them 2 separate regions rather than 1 region?
Yes, so that's a good question. Ideally, what we want to do is when you have these winning regions, you want it to be winning in the remaining graph. So if you, okay, what this means is if you take this region, this contains an edge which escapes to a 3. So somehow I want to control that, the number of high odd priorities it sees before like being in a winning region. If that makes sense. So I didn't define this very clearly because if I did...
You sort of first say that right thing is a winning region,
yes.
Then you cut it off, and now the left thing is a winning region.
Yeah.
Right.
Exactly. So you want winning regions in the remaining subgraph such that you don't see any odd priorities from there. So like if I start a token, leave a token in this winning region and in the first winning region, and I ask Steven to play, then Steven either wins by staying within this region. If at all he leaves, then he immediately can only escape to CF4 if that happens. That makes sense. So just that the first winning region is kind of, you make sure that it doesn't see a 3 before staying here. Maybe I should stop explaining this and then go to the tree of an attractor decomposition. But yeah, that is a good question. You want to just make sure that if you start a play, you want it to remain in one of, if it remains in one of the subtrees, you don't want it to see like a high odd priorities, sub games. So now we'll define tree of an attractor decomposition, and it's defined as follows. If your attractor decomposition was trivial in that it just contained an attractor to a high even priority, then you have the attractor decomposition of that would be just a dot or like 1 vertex. If not, you have this structure that we talked about before of you have attractor to D, and then you have a lot of sub games, each of which will have its own attractor decomposition, which you will put together in like this ordered fashion and form an ordered tree for every parity game. So this is why we will talk about trees and parity games in some sense in the rest of the talk. So now I think the time is, yeah. I'm just keeping an eye so that I don't run out. So now we're back to what many quasi-polynomial time algorithms look like. So we're now ready to define what a universal tree is. We know what an ordered tree is. It's just a tree where the edges occur in some order, and a universal tree is just a large enough tree such that, in this case, we'll call it an NH universal tree, such that it has height h first, and it can fit any tree with any ordered tree with n vertices in it. So here, if you look at this tree, then if you take any tree with, like, this is a 4-2 universal tree, what this means is if you take any tree with height 2 and at most 4 leaves, then you can fit that over here. So above are some examples in pink, and you can try to fit each of these trees over here. So the first one fits like this nicely, and the next one can say fit like this one, say fits here, and the next one fits here, and so on. I mean, this is just an example, but I can assure you that this is 4-2 universal, and if you come up with any tree with 4 leaves, you can actually fit this in here. Now, this is what quasi-polynomial time algorithms, many of them do, in that they look for the tree of the parity game somehow hidden in this universal tree by actually exhaustively searching through this universal tree. So we might say, oh, so that's great. So if we can get smaller universal trees, then shouldn't we get faster algorithms for parity games? But unfortunately, that is not the case, in that there is a combinatorial result that was proved by Shevensky et al. In 2019 that said, okay, so if at all you have a universal tree, which is ND universal, then that universal tree should have size at least quasi-polynomial. So this smashes our hopes for improving any of these algorithms by making small tweaks if they have like a universal tree embedded in them. And unfortunately, it is most algorithms that actually have a universal tree embedded in them, and that had been pointed out again by Shevensky et al., which said Kalud et al., which is the breakthrough result, has a universal tree because it produces something called the separating automata, and every separating automata has a universal tree underlying it. The next one was Yudinsky and Lazar's paper in 2017, which was called the progress measure algorithm. And that also almost explicitly produced a universal tree, so there was no need to search for one hidden in there. And later on, for a while, Paris came up with this McNaughton-Zelonka type algorithm, which is just computing attractors in a specified manner so as to produce winning sets for both players. It seemed that this immediately did not have a universal tree hidden there, but I mean, Paris, along with there was an improvement of Paris by Letnin, Chevet, and Wojciech, which also used some recursive attractor type algorithms. But it was shown later on by, again, in a 20 paper that you, in a paper by Yozinski and Morvan, that you can actually generalize these two by as taking as input a parity game and very fixed universal trees, and actually the computing these attractors as dictated by these universal trees. So like doing this was equivalent to that. And you can see that there is a blue arrow on the side that was just to say that these are two different kinds of algorithms, progress measure and attractor decomposition. And towards the end, I will talk about a hybrid of these. And we'll again come to the reason why we do these later on. But maybe what I really want to highlight in this is this algorithm by Lettinen in 2018, which did something called, which used something called register games to solve parity games in quasi-polynomial time. And what did that do? Well, very roughly, the idea of that algorithm was as follows. I'm not going into too much detail. Is it took as input a parity game as usual, and somehow it also had another input which we will call k, which is a mysterious number, which if given as input, it constructed a large parity game which had n times d to the k many vertices. So like if k is large, and this is like pretty large, but you note that the number of priorities is at most 2k plus 1 in this huge game that Lettinen had constructed. So from this, in this large parity game, even if you used an exponential time algorithm, you would be able to solve it in time n times d to the O of k square, let's say. So even by using naive algorithms, you would get this. And what was the highlight of Lettinen's result was that she was able to show that if you input k as log n, well, log n plus 1, then the solution of this large parity game is in fact equivalent to the solution of this small parity game. And that kind of gives you a quasi-polynomial time algorithm naturally if you just substitute k equals log n in this result. So now, why is this important? Well, if you look at just this, n times d to the O of k, if k somehow were constant, then you get a polynomial time algorithm, which is very important. So it makes sense to ask, what are these games for which you have constant or small k? Because these are games that can be solved really quickly by this algorithm. And you can also ask, how do they fare using other algorithms? So if you, for instance, take k equals 1, what happens is if this huge circle denoted the set of all parity games winning for Steven, all winning games. So then k equals 1 would solve a small set of games. And then when you substitute k, when you put k equals 2, you solve an even larger one. And so on until when you give k equals log n plus 1, then you kind of solve all games for Steven. But this diagram is quite misleading in that, in fact, it's true that this k equals 1 is not as small as we think it is. And we were able to show some cute, this is just a cute result, which just says, if you choose, random is heavily asterisked. So if you choose a random parity game chosen carefully via some methods, in fact has register number or this k value equals 1. And like we even had some master students who implemented this and some version of our algorithm, which showed that most of the things that they were working on, like real life parity games, have k value at most 3 or 4. So this is definitely a fundamental parameter. So I'm sure I've convinced you all of that. So what are we here to talk about? Well, maybe first it makes sense before I go into my results to talk about how rivers are named. So this is where Strahler number comes in. I swear I'm not digressing. So have you ever wondered if, like, when two rivers meet, how they name the resultant river after one of the two rivers before? So, when Ganga and Brahmaputra meet, the resultant one is called Ganga, but we don't know why it's not called the other river. And this is because in hydrogeology, they had like this concept introduced by Stroller, well, defined properly by Stroller, which gave a way of numbering river systems in general. And how they do this is as follows. The sources of these rivers are given value 1, as you can see over here. So I'm going to erase this and fill it up in real time. So the sources of these rivers have Strahler number 1. And when two rivers or more meet at a node, then what happens is the resultant river or node gets Strahler number maximum of its children if the maximum is unique, and if not, it gets maximum plus 1. So in this case, all of these nodes at the second level get Strahler number 2 because they have 2 or more children and all of them have Strahler number 1, so nothing is unique, so it gets maximum plus 1. Whereas over here, let's say this node also gets Strahler number 2 because it has only one child, so its maximum Strahler number of children is unique. So it doesn't have the plus 1. Whereas this one would get 3 because it has 2 children and the maximum is not unique. So the Strahler number of the whole river system, like on the top, would be 3. So now when two rivers meet, they are actually named after the river with the higher Strahler number. So this is somehow capture the branching depth or like complexity of a system. And there are many uses of this in computer science, and there are you should see this paper by Vieno, and there is like an expository one by Javier Esparza about Strahler number. So all of these are good reads, I would say. Now we go on to talking about Strahler number of a parity game, which was half the title of the talk, if not more, is, as you would imagine, the Strahler number of the tree of attractor decomposition, well, with asterisks because there is some min and max, because a decomposition need not be unique. So you take the min of the Strahler number of all possible decomposition trees and for each player, and then you take the max for both the players to define the Strahler number of a parity game. So if this is confusing, you can just imagine that this is the Strahler number of a decomposition just for like, the stock, but this comes with a caveat is all I would like to say. So why am I talking about Strahler numbers? Well, we were able to show that that K value that Lehtinen had introduced in her paper was in fact equal to the Strahler number. And this was surprising because there was no initial way of looking at her algorithm and immediately seeing either a separating automata or a universal tree in it. But this gave away because now, if you remember, there was this picture which said most quasi-polynomial time algorithms look like they had a universal tree in it, and it is now true that faster implementation of Lehtinen's algorithm in fact also would have a universal tree in it, because the K value that she inputted was in fact log n plus 1, because it is the Strahler number of a tree with n vertices, which can be at most log n. So now what we were able to do is, come up with small Stroller universal trees. And what is a Stroller universal tree? Well, a K Stroller NH universal tree is a tree which has height h, but can embed any tree which is small in terms of number of nodes, as in it has at most n nodes, and Strahler number is also restricted. So previously you saw a 4-2 universal tree, but here is a 2 Strahler 4-2 universal tree. So this is, if you look at the tree above, you can actually embed that, which has Strahler number at most 2. You can embed that nicely into this 2 Strahler NH universal tree. Okay, so, and we were able to show that there are K Strahler NH universal trees of size as follows, which is polynomial in n and h over k to the k. So I realize that I have around 10 more minutes. So I'll quickly move on to our results part 1, which may be the more interesting part. Is if you we were able to come up with an algorithm that ran in time as follows, which was a significant, this over here, and this was a significant improvement to, say, Lehtinen's algorithm. But not only that, what our algorithm also did was increase the class of parity games in which you can have a polynomial time algorithm. So previously, you knew if D was like log n from Kalud et al., and you knew that these kind of parity games could be solved in polynomial time. And Lehtinen showed that if K was constant, then you can also solve these parity games in polynomial time. But now we were able to show if this equality holds. For instance, equality is in if K times log D over K is like log n, this is a super class of both of these, then you still have a polynomial time algorithm for parity games. So now we finally want to talk about, we have seen Strahler number and how it is impactful. But what this also highlights is you might have several classes of parity games with smaller trees than the typical universal trees that you have, which we saw was the reason these algorithms took a quasi-polynomial of the time, all of it. So it makes sense to design newer algorithms which for which you can modify the input trees rather than assuming that the underlying trees are universal. And this is what I hope to talk about my other work very quickly, in that, so what we were able to show is, so one of the work is the following. you have McNaughton-Zalonka's algorithm, which I briefly mentioned before, which computes attractors recursively and runs in exponential time. This was one of the first algorithms to solve parity games, and it takes exponential time. But what I didn't mention about this algorithm yet is that when it comes to implementation, this seems to run faster than pretty much all known quasi-polynomial time algorithms in practice. And none of those which have faster running time seem to be able to beat this yet. And we would like to find out, first of all, why, because I mean, this seems to have exponential running time, but seems to perform so well in practice. And uh, later on, I also mentioned Paris and his improvement algorithm by Letinencheve and Wojciech, all of which also computed attractors recursively. And in a recent work which which we've just submitted, we were able to, in this paper, uh, talk about an attractor decomposition algorithm, which kind of not only extends these, which kind of uses universal trees as input to solve this. So you can tweak these universal trees, in fact, to contain smaller trees, and also solve something called nested fixed point equations, which I will not go into detail to, somehow inspired by attractor computation. But what these algorithms do is, instead of take as input two universal trees like the previous ones did and compute like a fixed partition, what these do is take as input smaller trees, and instead of always giving you the right answer, it has some guarantees. So if your parity games have, if you're, okay, maybe yeah. So if you have a parity game whose underlying tree can in fact embed into your input trees, then your algorithm will give you the right answer. And in fact, there is a stronger guarantee that if this box over here is the, let's say, Steven's side, uh, is the set of all games that you can, set of all vertices that can be embedded into this tree, input tree, then, and this is the set of all vertices that can be embedded into that tree, what this algorithm produces is some kind of a partition between these two winning sets. But we don't know where exactly this partition would lie, which is where the problem is, because if you don't give universal trees, there will be some games for which this gives you the wrong division between even and odd. But if you are able to guarantee that your input trees can contain the trees of this game, then your algorithm would run correctly. And this runs in time product of two trees times polynomial in n. So this is all attractor based algorithms. But the downside of attractor based algorithms is that they actually run much slower than what we call progress measure algorithms. So if you remember, long ago, there were two types of these. When I say run slower, I mean, theoretically, there is a quadratic factor hidden inside, it's the attractor-based algorithms are pretty much square of progress measure algorithms. For instance, Yudinsky and Lazar's algorithm ran in time linear in the size of the tree rather than quadratic in the size of the tree. So our next work with Marchin and Morven and Ullman was the following, where we kind of gave a hybrid algorithm which ran in time minimum of the even tree and the odd tree times a polynomial. And this minimum is quite a decent breakthrough because it does compute attractors. So we haven't really done the real work of implementing it yet, but we hope that by computing attractors, it will run faster in practice, as did McNaughton-Zalonka. And since it has this minimum factor, what you can do, like, you have theoretical guarantees that it will run faster than these attractor-based algorithms, which have a quadratic time. So this is the work that I had done with my co-authors so far. I think I should stop now and ask you to ask me questions so that we can have more interesting discussions. Thank you.
Thank you very much, Thejaswini. If there are questions, please. And by the way, yes, thank you so much for this very nice and interesting talk. I really appreciate it.
Thank you.
No question?
So this is maybe a kind of dumb question about your very last thing. So if I have a game where it so happens that every vertex is a win for even, but for really complicated reasons, this is kind of saying you can do that in just polynomial n time. Is that right? Or is
it's
is
kind
that
of like
because it kind of can't be for really complicated reasons if every vertex is winning for even or something?
But this kind of assumes that you know that this is winning for even in the beginning. So if someone tells you all vertices are winning for even, then you can tell all vertices are winning for even quickly. So this is kind of
I see.
trivial. So this does not give a strategy or a witness. So it's difficult to verify if your algorithm, I mean, the algorithm does not produce like, say, an attractor decomposition, which would say, yes, here is these sets are winning and here is your thing. All it does is produce a partition. So if you already know that your input algorithm satisfies some criteria, then you can get this partition correctly. So the correctness of this partition is just, I don't know if I answered your question, but since you already assume
I see what you mean. You have to input some sets of trees which you know are going to contain the right ones. Yeah.
Thank you. Other questions?
Sorry,
I can't hear you, Raghavan. I can't hear you.
Can you hear me now?
Yes.
Okay, great. Hi. Thank you for a nice talk. I'm just wondering, can you give some idea about what kind of applications then you're interested in, like actually solving these parity games for? I mean, basic question.
Yeah, so maybe I should have led with why people look at parity games other than the complexity perspective. But parity games, for instance, are known to be polynomial time equivalent to solving model mu calculus. And it has several applications in logic in general and automated theory for checking non-emptiness of several tree automated stuff. So in general, parity games are well studied because they are useful. There are several like it's used in synthesis and verification.
Right, I see. Yeah, and maybe model checking, or is that
yes, it is in fact.
Okay, that's great. Thank you.
Thanks for the question.
Are there other questions?
Maybe I could ask then. Thanks for the nice talk, and you explained that in practice the Strahler number is surprisingly low, and this allows you to use smaller Strahler universal trees instead of full universal trees. And is there any fully established, or at least assumed size dependence, like how Strahler number k to which size of the universal tree it leads, so that to see how it goes from very small to the full universal tree?
Yes.
Okay.
So
okay.
If you have a k Strahler and its universal tree, there is an exponential dependence on k, but if you have things up till 4, you'd still have a nice.
Yeah, and yes, this you claimed as an upper bound, and do you expect this to be tight?
We actually have a lower bound as well, which we're still writing up for our journal version, but it is not published yet. Yes.
Yeah, so but basically it's tight. Okay.
It's almost, yeah, like the polynomial is different, but it's quite tight. Like in
Well,
yeah,
I mean,
yeah.
who optimizes polynomials when
Exactly.
you have such a nice exponential?
So I think if I'm not wrong, there is a h to the k minus 1 lower bound. H. Yeah.
Yeah. Thanks.
Other questions? Well, if not, thank you again, Thejaswini. And
thanks a lot.
thank you all for coming
pleasure.
today. Unfortunately, we were not that numerous, not as usual, not as many as usual. I hope that we will have more people coming next time. And thank you again, Thejaswini.
Thanks a lot.